All right, this is going to give us a relationship between a line integral and a double integral. Okay, so it's Green's theorem. If the curve C is a positively oriented, piecewise smooth, simple closed curve in the plane, and D is the region that's bounded by that curve, then if P and Q have continuous partial derivatives on the open region that contains D, then the line integral of P dx plus Q dy can be converted to a double integral over the region D. Take the partial of Q with respect to x minus the partial of P with respect to y dA. Now, I'll give you a chance to write that down, then I'll tell you what a positively smooth, simple, closed curve is. And this is actually in your book. It is on page, Green's theorem is on page 1136. In the box in the middle of the page. And the reason you would want to convert this is because sometimes it's easier to use Green's theorem than it is to do the line integral. Yeah, and I put the notation down here. If you see an integral with a little circle on it, that means that this is a closed, simple closed curve, and that it may or may not be positively oriented, but it is a simple closed curve. So you're still writing. But the positively oriented curve means it goes counterclockwise. It goes in a counterclockwise direction. That is positively oriented, which to me seems backwards, but that's the way it is. The smooth curve, if it's piecewise smooth, it is smooth in pieces. It would go like this. It can come to a point, and then it can be a smooth. This piece is smooth. This piece is smooth. It has no gaps, no weird things going on. It's just nice smooth curve, like it would say. If it is simple, then the curve does not cross itself. So something like this is not a simple curve because it crossed itself. If it is closed, then the starting point and the ending point are the same. It starts and it ends in the same place. It would go in a counterclockwise direction. You would go from here to here. This is a simple closed curve. This is the region D that is inside the curve. So you're changing a line integral over something like this to the area of the region that's enclosed by that. Because you know, if you have a line integral and it's not conservative, then you have to find the parametric expression for this curve. And sometimes that can be tedious, especially if you have something that goes like this, and then something that goes like this, and then something that goes like this, and if it went all the way back to there. You'd have to find a path for this, a path for this, a path for this, and a path for that, and do 4 different pieces. Yeah. But it might be easier, not sure it would be, if you could find that it convert it to a double region and do the integral of that. That's kind of the idea of what we're doing here. Okay? If your curve is not positively oriented, then all you have to do is do the negative of your answer. So if your curve goes the wrong direction, in the end, just make your answer negative. Just swap it. Make it negative. Okay, let me look at a couple of examples. And on these, you have to draw your picture because you've got to make sure you have a closed curve and that it doesn't cross itself. So let me look at maybe number 4. And this says that it's a simple curve. X squared y squared dx plus xy dy. And C is the arc of the parabola y is equal to x squared from the point 0, 0 to the point 1, 1, and the line segment segments from the point 1, 1 to 0, 1, and from 0, 1 to 0, 0. So this is the curve. This is the P dx and the Q dy. So when you look at the graph of your curve, y is equal to x squared from the point 0, 0 to 1, 1. That's that much of the parabola. Then you're going from this point to the point 0, 1. So then I'm going this direction. So I'm headed this direction. And then I'm going from 0, 1 back down to 0, 0. Okay, that is a simple closed curve. And it is positive oriented because it's going counterclockwise from beginning to end. So if you did it the old-fashioned way, from 6.1 or 6.2, you'd have to use this path, plus this path, plus this path, parametric equations, add them all together. But since it's a simple closed curve, it is easier just to change it to a double integral and integrate like you would any double integral. So you've got to find your limits of integration for your x and your y. So I would let y go from here to here. So y is going from this line, which is x squared, to this line, which is 1. And then x is going from 0 to 1. Now if we're changing it to using Green's theorem, you need to take the partials of these things. Now the formula says you take the partial of q with respect to x. So the partial of q with respect to x is y. I need the partial of p with respect to y, which is 2x squared y. And the line integral is the double integral from 0 to 1, from x squared to 1, y minus 2x squared y, dy dx. And that to me is a lot easier than doing piece 1 plus piece 2 plus piece 3. Okay, so whatever we get when we integrate this, and I do not know. That's not right. Yeah, I couldn't even type it in right. For some reason I thought I needed to put a Z in there. Did y'all get 1 over 15? Uh-oh, you didn't get that. I'll be finished then.
I got a negative.
You could get a negative answer. What did you get, Tori? That's what I got. I got 22 over 105. But I was typing and I made one mistake, so I may have made another one. Oh, you did? Oh, okay.
No, I got 3 over 5.
Hey, I'm not sure if you're getting closer or further away, but Well, we're going to assume the girls are right today. Okay.
So, anything
22.
Yes, we're just going to assume that the girls are right because we usually are. But anyway.
anything with your y or your dy is going to be q.
I'm sorry, anything with your dy is what?
It's going to be q.
Yes, this is your q. Yes, I'm sorry, I was lost for a minute. This, yeah, because it's with the dy.
Okay.
And the p is with your dx.
All right, because you all of a sudden you lost me when you did dq, and now I realize that you did that one first. Yeah.
I did that because I was subtracting in that order. You could do it the other way, but I knew I was going to subtract q minus p.
You're fine.
Okay.
I was doing it in my head that the first one would have been q and the second one would have been p. And
Back.
that's-
That doesn't work.
Yeah, no, and I figured that out real quick.
Okay. All right.
It's always q minus p.
Partial of q with respect to x minus partial of p with respect to y. Yes, always that. All right, let's look at maybe number 10. The line integral of 1 minus y, to the third, 1 minus y to the third dx, x to the third plus ey squared dy. And C is the boundary of the region that's between the circles. X squared plus y squared is equal to 4, and x squared plus y squared is equal to 9. So your region C is between two circles. Circle of radius 2 and a circle of radius 3. So this is your region right here. So when you do this double integral, it is going to be best done if we switch this to polar coordinates, because this is a circular region. All right, this is still P, and the second one is still Q. But I'm going to put this in polar coordinates, so I'm going to go ahead and do my limits of integration with r's and thetas. I know that r in this case is going to be going from 2 to 3, and theta is going all the way around from 0 to 2 pi. I'm going to do my partial of q with respect to x, which is 3x squared. The partial of p with respect to y is negative 3y squared. And when I do 3x squared minus negative 3y squared, I'm going to get 3x squared plus 3y squared, which I need to change to polar coordinates. Are y'all following me before I put it in my integral? So this would be 3x squared plus y squared, which is 3r squared. So when you do your polar coordinates, the integral from 0 to 2 pi, the integral from 2 to 3, I have the 3r squared. When you do polar coordinates, add your extra r, put your extra r in there. This is my dr, and this is my d theta. And again, it makes the integral a whole lot easier than if it's a regular line integral. And we're going to see if the girls can get it right again this time. Probably not. At least not me. Times 2 to the third. Okay. Did you get 195 pi over 2? Oh, even the boys got it this time. Good. Okay, I was going to do one more because they just phrase it like doing F dot dr, just so you'd know that you'd actually do it the same way. So one more, I'll do number 12. Did you get that, Constance? Okay. Okay, number 12. It says use Green's theorem to evaluate F dot dr. And in number 12, my f of xy is the vector e to the negative x plus y squared, e to the negative y plus x squared. That's my vector. And c is the arc of the curve y is equal to the cosine of x from negative pi over 2, 0 to pi over 2, 0, and then the line segment from the point pi over 2, 0 to the point negative pi over 2, 0. All right, y is equal to cosine x. This is just a regular trig graph. This is not the polar graph. This is the regular trig graph of the cosine curve. So the cosine curve, negative pi over 2 to positive pi over 2. At negative pi over 2, 0, it starts here, it goes up to 1, and then it comes down here. So this is the cosine curve. From negative pi over 2, 0 to pi over 2, 0. Then you have the line segment that goes from here to here. Notice the direction they told me to go. Is this the clockwise orientation? I mean positive orientation, I'm sorry. It is not the positive orientation, it is the negative orientation. So whatever we do with our answer, whatever answer you get, just multiply by -1 to get the orientation correct. All right, so we're going to change it to an integral over that region because it is simple and closed. So I would let my limits of integration, my y is going to go from this line to this line. So this is from 0 to the cosine of x. And my x's are going from negative pi over 2 to positive pi over 2. This is not polar coordinates. This is not r's and thetas. This is x and y's, okay? All right, going back up here, this is f dot dr. But all you have to do the p and q thing, this is p, this would be q. So take the partial of q with respect to x, which is 2x. The partial of p with respect to y is 2y. And then just do this one minus this one, the double integral, from negative pi over 2 to positive pi over 2, from 0 to the cosine of x, 2x minus 2y. This is dy and this is dx. And that would be our answer. The integral 2 times x plus 2 times y. Okay, when I evaluate this, I got negative pi over 2, but I need the opposite orientation, so that makes it plus pi over 2. Because it was in a negative direction instead of a positive direction. Okay, that is Green's theorem. Do you have a question? No? You're good? Okay.